Okay, so for this next video, I want to talk about a subject which is quite common in the field of robotics, but I think needs to be clarified within RoboDK if you don't want to waste some time just not understanding how RoboDK shows certain data and potentially looking for issues or mistakes that do not exist, and I would hate for you to waste some time with that. So I'm going to open my normal online library, local library, sorry. I'm going to bring in two robots. So I'm going to bring in a normal, let's say, KUKA robot, standard KR6, KR6R900, and I'm going to bring in a UR robot, so UR5E robot. Okay, so I have both like that. Perfect. If I double click on the robot here, nothing new here, we have the tool frame with respect to the reference frame. As we already discussed, we have here X, Y, Z, so we have the translation. Then we have our rotation. All robots, in fact, there's many ways of expressing an orientation in robotics. Those ways, if I can say, are called Euler angles. So EULER angles. They are a way to express a rotation of a reference frame in space. And the point is that each robot brand uses a different approach or flavor of Euler angles, if I can say. Not each brand, because some brands use the same kind of flavor of way expressing an orientation or an angle, but some have huge differences. So if I was to open the robot here, you will see what I mean. If I press plus a few times, here it is, and let's just rotate that 90 degrees here, and let's press plus a few times. Okay, so here we have in both cases the position of the tool frame, active tool frame. In this case, there's no tool in both cases, so here we were talking about the flange with respect to the base. Okay, so we have X, Y, Z, those differ, that's normal, they are not the same robot. And I rotated J6 of the UR 90 degrees. I'm just gonna switch that so that you have here UR and here the KUKA, so that you can better see. Okay. So anyway, the point is that here both my frame are in the same exact orientation. And if you look at the data here, you have 0, 90, 0 for the robot, the KUKA robot, and you have 0, 90, 0 in this case also for the UR. So that's kind of normal. I'm going to bring it here 90, so that's fine. But if I was to rotate, I don't know, like 90 degrees, the TM robot, the KUKA robot. So we are in this direction here, which means this represents the same orientation as the home position here. Now our Euler angle or rotation is represented by, in the case of the KUKA robot, minus 90, 0, minus 90. And in the case of the UR robot, minus 69.282, 69.282, and minus 69.282. And you will agree with me that this orientation and this orientation with respect to the respective reference frame is exactly the same. So why would that happen? So this is in part because, in fact, completely because of the Euler angle format or methodology they've been using. And you can see that Euler angle methodology here if you look at the writing just after the rot. So in the case of ABB, KUKA, and Nachi, The Euler angle format used, if you were to open up the controller, is z, y prime, x prime prime. What does that mean? This means a rotation around the z of the base frame, followed by a rotation around the y of the newly created frame, so this is why the prime comes in, and then afterwards a rotation around the x of the newly created reference frame. So I generally have here some tools that I'm using to explain that. Where are they? I don't see my little tools. That's a shame. Not a big issue. We'll just do it with frames. So I'm going to create a frame here, bring it in front of myself. And that means here, if we were to follow that here, a rotation of minus 90 around z, so minus 90. If there was no prime, that means that would have mean a rotation with respect to the original frame here. But as we have a prime, we're going to use that, let's say, first phase. Then 0 rotation, then a rotation of minus 90 with respect to the z-axis. So z-axis here, rotation minus 90, and indeed this newly created reference frame is exactly in the same orientation as this one. So I personally like this way of representing Euler angles. If I bring in, let's say, a Fanuc robot, basic Fanuc robot, and we open it up and just do a rotation like that, so minus 90, so that we have the same, oops, minus 90 here. If I was to look at it now it's minus 90, 0, minus 90, so it's the same exact result. But I'm going to show you where it differs. But in the case of Fanuc and Motoman, it's x, y, z. So it means it's a rotation with respect to the basic reference frame, followed, in fact, rotation with respect to the base of the robot, followed by again a rotation with respect to the base of the robot, followed by again a rotation from the base of the robot. So if I was to explain that here, if I bring in a new reference frame in front of it here, so that means first a rotation around the x-axis of the base, so rotation around the x-axis, minus 90 degrees, so minus 90, followed by a rotation around the z-axis, the basic z-axis of the base, so it means this one here, rotation of minus 90. So if we were to rotate of minus 90, this means in this direction here. And indeed, this does match with that. So those are kind of the steps you need to take to go from the frame from a frame here to the flange. So I don't want to give you like a course on how transformation matrix works. But the point, because this is, and by the way, this is very important in robotics, so if you don't know how this works, it can be a nice subject to explore on your end. The point is that you really need to be careful when you're using RoboDK, and that you're transferring information from either the robot to RoboDK, or from RoboDK to the robot, or if you're comparing information from one robot to the other, to make sure that when you're comparing the angle values, that you are considering how those values are represented here. And I very much want an emphasis on the fact that it's a representation. In the background, this value here, or this value here, or this value here are exactly the same. So for the robot program generation and stuff like that, there is absolutely no difference whatsoever. But you need to know, that here, even if you see that, it may mean that. So if you want to know what this means in another format, you just take the drop-down menu and you go see what it means. You can even see it right away here. So minus 90, 0, minus 90, ABB minus 0, 90, minus 90. So Staubli, it's a bit different. So 0, 90, minus 90. UR, you need to remember that you have UR rad and UR degrees, so the controller works in radian. So you need to take that into account. For ABB, you have the quaternions if you need them. Adept, Como, and I don't know which other brands. And Kawasaki uses Z, Y prime, Z prime prime. So rotation around the Z of the base, rotation around the Y of the newly created frame, and rotation around the Z of the newly created frame. You have Cacti SolidWorks, CRS, which I have no idea what it is, and then you can see it as a script. By the way, that's a cool little trick. I wasn't planning on showing you that now, but when you put it as a script like that, you can add some basic equation or addition, multiplication, division. So if you say, okay, I want to just add 153.5 here, press enter. Like in this case, it won't move because it's too much. Okay, so I'm going to go minus, let's say. So if I want to go minus like that, it did go back that value here. If you go back to UR degree, that value will be like the equation will be solved. And if you were to go back here, you won't have the equation anymore. You don't have the result. But that can be a cool way to just add some very specific information without having to go to a calculator and add them and then come back. So I'm not using that often, but when I do, I really appreciate it. Okay, so last thing real quick. So Euler angles are also important to look at here if you're doing like targets. If you're doing frames, they will also be part of how it's displayed. Generally, it will take the default Euler angle format of the robot brand for you. Here, what you can do here, if you go tool option, you have Euler angle here. If you're using generic, it will kind of adapt to the brand and stuff like that. But if you want, you can like decide to use one specific as your default option. That's something that you can play with if you like want to make sure that you're always using the same and that you don't get confused. But yeah, that's important. If I was to bring back here default UR degrees, if I was to rotate that like just at 90 degrees, oops, this is not the right one, but let's go for a 45-degree angle. So sometimes with UR it's a bit tricky to kind of find the right balance if you're using the UVW. Like here I thought I would be like straight, but if I go and click Fanuc, having the UR rad, the UR degree at minus 90, 90, and 95, and 45, which in my mind should give me like if I look at it quickly, it should give me something like a 45-degree angle, but it's not the case at all. Like it's really screwed a bit to the side. And if I go back to, I don't know, Fanning Waterman or ABB Kukonachi, I look here, I have like minus 87, 5.2, and then 121.3. That doesn't make sense. And if I enter here instead, like values that make a bit more sense, 90 plus, minus 90 minus 35 would give me 125. So now we have just a 45-degree angle like that, like minus 90, 0, 120, minus 125. But if I go back to UR degrees, like those values doesn't make it doesn't make any sense. Like it's really not easy to understand. So yeah, that's it. Hope it helps.